Hi all, this is Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process and the topic is Electrochemical Machining. Right. At the end of this session, student will be able to understand electrochemical machining process or procedure. Right. Introduction. Electrochemical machining, in short ECM, is a modern machining process that relies on the removal of workpiece atoms by electrochemical dissolution (ECD) in accordance with principles of Faraday. Okay, so during 1833, Faraday reported electrochemical machining is a modern machining process that relies on the removal of workpiece atoms by electrochemical dissolution as per the principles of Faraday. Okay, during 1833. Right. Next, Gusev introduced the first patent on electrochemical machining in 1929, and the first significant development occurred in the 1950s when the process was used for machining high strength and heat resistant alloys. Okay, so usually for high strength and heat resistant alloys, conventional machining process is very difficult for the material removal. Okay, so here this electrochemical machining plays a predominant role for machining high strength and heat resistant alloys. Okay, so that it has been reported by Gusev. Okay, he experimented and got patent during 1929, and he developed a significant contribution during the 1950s, that is exactly after the 20 years of his getting patent. Right. Principles of electrolysis. Okay, electrolysis occurs when an electric current passes between two electrodes dipped into an electrolyte solution. Okay. So here electrolyte solution is an important parameter. Okay. Electrolysis occurs when an electric current passes between two electrodes dipped into an electrolyte solution. Okay, now let us see what is these two electrodes. Okay, what is anode, what is cathode, and all these things. The system of the electrodes and the electrolyte is referred to as the electrolytic cell. Okay, what is electrolytic cell? The system of electrodes and the electrolyte is referred to as the electrolytic cell. Okay, next, the chemical reactions which occur at the electrodes are called the anodic and cathodic reactions. Okay, the chemical reactions which occur at the electrodes are called anodic or cathodic reactions. Okay, right. The amount of metal dissolved, that is removed by machining, or deposited is calculated from Faraday's laws of electrolysis, which state that number 1, the amount of mass dissolved in kg. Okay, here the amount of mass dissolved is m, is directly proportional to the amount of electricity. Okay, that is I and T, where I equal to electrolyzing current in amperes and T machining time in minutes. Okay, so let us discuss once again this point, Faraday's laws of electrolysis. the amount of mass dissolved is directly proportional to the I and T. Okay, so what is I? Amount of electricity or electrolyzing current in amperes, where T equal to machining time in minutes. Okay, right. Second principle, the amount of different substances dissolved by the same quantity of electricity, that is IT, is proportional to the substance's chemical equivalent weight, that is zeta. Okay, so here M is directly proportional to the chemical equivalent weight. Okay, that is zeta, and that is equal to A by Z. So where I equal to electrolyzing current in amperes. So in the previous slide, okay, M equal to IT. Here uh, M is directly proportional to INT, and M is directly proportional to zeta, and zeta equal to A by Z. Okay, now let us see what is what. Okay, so I equal to electrolyzing current in amperes, and T equal to machining time in minutes, and zeta equal to chemical equivalent weight, that is G into grams. Okay, means grams. A means atomic weight, this one. Z means workpiece valence. Okay, so here second Faraday law imply that M is directly proportional to zeta and zeta equal to A by. Next, theory of ECM, electrochemical machining. Electrochemical machining uses a direct current at a density of 0.5 to 5 amperes per square millimeters and a low voltage of 10 to 30 volts. Okay, so here the voltage is 10 to 30 volts only. Okay, and high current density 0.5 to 5 amperes per square millimeters. Okay, the machining current passes through the electrolytic solution that fills the gap between an anodic workpiece and a pre-shaped cathodic tube. Okay, already we have discussed that workpiece is anode and tool is cathode negative. Okay, the machining current passes through the electrolytic solution that fill the gap between the anodic workpiece and the pre-shaped cathodic tube. Okay, right. The electrolyte is forced to flow through the interelectrode gap at high velocity, usually more than 5 meters per second. Okay, so here the electrolyte velocity is very high, that is 5 meters per second, to intensify the mass charge transfer through the sublayer near the anode. Okay, so here the electrolyte is forced to flow through the interelectrode gap at high velocity, which is more than 5 meters per second, to intensify the mass charge transfer through the sublayer near the anode. The electrolyte removes the dissolution products such as metal hydroxides, heat, and gas bubbles generated in the interelectrode gap. Okay, so here the electrolyte removes the following dissolution products: hydroxides, that means metal hydroxides, heat, and gas bubbles. Okay, Right. During 1988, Megoff claimed that when a potential difference is applied across the electrodes, several possible reactions occur at the anode and the cathode. Okay, so when the potential difference is applied across the electrodes, obviously reactions will be occurring at anode and cathode. Okay, so that's what we are experiencing during 1988. Megoff claimed. Okay, this one. Right. Figure 1. Electrochemical reactions during ECM of iron. Okay, so figure 1 illustrates the dissolution reaction of iron in a sodium chloride water solution as an electrolyte. Okay, so okay, look at this figure. This is electrolyte. Here cathode is negative and anode, the workpiece, is positive. Okay, so here hydrogen gas H2, and here this is ferrous hydroxide FeOH2. Okay, now how this chemistry is taking place. Okay, so 2H plus 2E that equal to hydrogen will go up. Okay, so this hydrogen will go up. Okay, here iron means Fe. That's what we are discussing here. Okay, for iron. Okay, Fe plus 2OH equal to FeOH2. Okay, that goes down. Okay, so these two are going in opposite directions. Okay, so here hydrogen gas is going up and FeOH twice is coming down to the workpiece. Okay, the result of electrolyte dissolution and NaCl dissolution leads to like this H2O. Okay, H plus OH minus NaCl, Na plus Cl minus. Okay, so this is the basic chemistry of the H2O and NaCl when dissociation is taking place. Okay, the negatively charged anions OH minus and Cl minus move toward the anode, and positively charged cations of H plus and Na plus are directed to the cathode. Okay, so here anions and cations. Okay, so anions means negatively charged anions. Okay, OH minus this one and Cl minus this one move towards the anode. Okay, why? Because these are negatives, so it will move towards the positive. Okay, and the positively charged cations, okay, these two, okay, H plus and Na plus are directed towards the cathode, that is negative one. Okay, right, at the anode Fe changes to Fe plus plus by losing 2 electrons. Okay, so this is the equation of dissolution. Okay, Fe gives rise to Fe plus 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 2 electrons. Okay, right. Here the chemistry is completely a pair of positive and negative. Since your elementary school studies and even intermediate level, you have been crossing all these chemistry equations. So here also the same chemistry is applied. Okay, right. At the cathode, the reaction involves the generation of hydrogen gas and the hydroxyl ions. Okay, hydrogen gas and the hydroxyl ions. See, look at here, hydrogen gas and hydroxyl ions. Okay, so when water plus 2e, that is 2 electrons, okay, gives rise to hydrogen gas and plus 2 times OH minus, okay, hydroxyl ions. Okay, the outcome of these electrochemical reactions is that iron ions combine with other ones to participate out as iron hydroxide and FeOH2. Okay, look at here, Fe plus water, okay, hydrogen gas and FeOH2. Okay, next, the ferrous hydroxide may react further with water and oxygen to form ferric hydroxide. Okay, FeOH2 will become FeOH3 here. Okay, look at here, FeOH2 plus water, again it is reacting with oxygen O2. Okay, that's what we have stated. The ferrous hydroxide FeOH2 may react further with the water and oxygen. Okay, water and oxygen to form ferric hydroxide. Okay, so this is ferric hydroxide. Okay, right. With this metal electrolyte combination, electrolysis has involved the dissolution of iron from the anode and the generation of hydrogen at the cathode. Okay, during 1974, Magoff reported. Okay, right. So this is completely a chemical reactions application only. Next, ECM equipment. Okay, so figure 2 shows the ECM elements. Figure 2 shows the main components of the ECM machine. Okay, the feed control system, the electrolyte supply system, power supply unit, and the workpiece holding device. Okay, look at this figure. Okay, so this is workpiece, that is positive one. Okay, so here DC power supply. Okay, power supply is 2 to 30 volts, that is DC. Okay, workpiece is fixing on a fixture. Okay, now we are applying constant feed. Okay, this entire setup is in the housing. Okay, we are providing a fan. Okay, this is short circuit protection. Okay, this is flow meter, pressure gauge, heat exchange, filter, pump, and tank. So this is sludge removal. Why? Because this is a completely a cyclic process. So from this tank, this medium, that is nothing but electrolyte. Okay, so that is nothing but complete electrolyte supply system. Okay, so this is electrolytic supply system. Okay, so that will circulate into the housing, and from that housing again it will come back into the tank. Okay, some filtering process will be taking place at this tank also. A pump is using in order to pump this what is that called, electrolyte. Okay, so here filters will stop the any debris which is coming from the workpiece. Okay, and a heat exchanger is provided in order to heat exchange, and flow meter in order to maintain the flow, and pressure gauge regulates the pressure of the electrolyte. Okay, so this is overcut and this is insulation. Okay, so here the workpiece is fixed to the fixture, and the ECM equipment uh, shows the machining process with some overcut and undercut. Okay, right. As shown in figure 3, the feed control system is responsible for feeding the tool at a constant rate during equilibrium machining. Okay, so here feed rate. Okay, feed rate, constant feed control system, machining chamber. On this machining chamber, we are attaching electrolyte system and power supply. Okay, and in this type, concentration, pressure, rate, temperature of the electrolyte system have been mentioned here. And in the power supply system, volt, waveform and current are the parameters associated to this power supply system. And here workpiece holding system is provided, and this is the machining chamber. Okay, so here the same thing has been reflected here in the figure 3 in order to show the feed control system, okay, which is responsible for the feeding the tool at a constant rate, okay, during equilibrium machining. Okay, see, look at here, constant feed will be providing, okay, in order to remove the material from the workpiece. Okay, right. So these are the various parameters. Mainly constant feed control system is responsible for the machining rate. Okay, and here workpiece holding system supports the workpiece. Okay, and power supply system is meant for the supply the power system with certain voltage and current, which are significantly play a role in the electrolyte flow system and all this. Okay, so electrolyte system is having with these three: temperature, pressure, rate, and type, concentration. Okay, right. The power supply drives the machining current at a constant DC, that is continuous or pulsed voltage. Okay, the power supply drives the machining current at a constant DC voltage. Right. The electrolyte feeding unit supplies the electrolyte solution at a given rate, pressure and temperature. That's what we have discussed here. Okay, pressure, rate, temperature. Okay, so here electrolyte will have to be feed or supply with the appropriate requirement. Okay, the electrolyte feeding unit supplies the electrolyte solution at a given rate, pressure and temperature. Why? Because this will be directly imply for the material removal. Facilities for electrolyte filtration, temperature control and sludge removal are also included. ECM machines are capable of performing a wide range of operations such as duplicating, sinking and drilling. Okay, so here electrochemical machining machines are capable of performing a wide range of operations including sinking, duplicating and drilling. Okay, right. Semi-automatic and fully automated facilities are used for large size machining such as deburring in the automotive industry. Okay, so here in automotive industry we are using semi-automatic and fully automated facilities, okay, for large size machining such as deburring. Okay, ECM machines, in contrast to conventional machine tools, are designed to stand up to corrosion attack by using non-metallic materials. Okay, so ECM machines, in contrast to conventional machine tools, are designed to stand up corrosion attacks by using non-metallic materials. Okay, so regarding power supply, right, the DC power supply for ECM has the following features: voltage of 2 to 30 volts, pulse or continuous, current ranges from 50 to 10,000 amperes, which allow current densities of 5 to 500 amperes per square centimeters. Third one, continuous adjustment of the gap voltage. Fourth one, control of the machining current in case of emergency. Fifth one, short circuit protection in a matter of 0.001 seconds. So see how fast that it will act. Okay. Sixth one, high power factor, high efficiency, small size and weight, and low cost. Okay, so just let me reiterate these power supply parameters. Voltage of 2 to 30 volts. Okay, it may be pulsed or continuous. Okay, current 50 to 10,000 amperes, and current densities 5 to 500 amperes per square centimeters. And regarding that gap, continuous adjustment of the gap voltage. Okay, control of the machining current in case of emergency. And look at this time, short circuit protection in a matter of 0.001 seconds. So electrolytes, the main functions of the electrolytes in ECM are to: first one, create conditions for anodic dissolution of workpiece material, conduct the machining current. Third one, remove the debris of the electrochemical reactions from the gap. Fourth one, carry away the heat generated by the machining process. Fifth one, maintain a constant temperature in the machining region. Okay. The electrolyte solution should therefore be able to ensure a uniform and high-speed anodic dissolution, avoid the formation of a passive film on the anodic surface, okay, and electrolytes containing anions of Cl, SO4, NO3, ClO3 and OH are often recommended. Not deposit on the cathode surface so that the cathode shape remains unchanged. Have a high electrical conductivity and low viscosity to reduce the power loss due to electrolyte resistance and heat generation, and to ensure good flow conditions in the extremely narrow inter-electrode gap. Be safe, non-toxic and less erosive to the machine body. Sixth one, maintain its stable ingredients and pH value during the machining period. Have small variation in its conductivity and viscosity due to temperature rise. Last one, be expensive and easily available. So these are the reference associated to this topic. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.